Welcome to Fun with Physics! Today we learn about rotational inertia. Our goal today is to determine a rotational analog for the equation F equals ma, or Newton's second law. First, let's consider the example of a force acting tangentially on an object that its center of rotation is on r distance away. If we consider that example, and we start with the equation F equals ma, we can assume that the acceleration of this point mass is a equals r alpha. Plugging a equals r alpha into F equals ma yields the equation F equals mr alpha, and multiplying both sides by r equals rf equals mr squared alpha. Now rf might be quite familiar to you. Rf is equal to torque. Therefore, we can rewrite this equation into torque equals mr squared alpha. Now that should seem even more familiar, as torque is the analog for force, alpha is an analog for acceleration, therefore mr squared should be the analog for mass. And we have come to our point of rotational inertia. So the equation for rotational inertia, or the most general equation, is I equals mr squared. Now if we take into account all the point masses in a system, then I equals the sum of mr squared. And finally, for a continuous body, I equals the integral of r squared dm after you integrate this equation. So, a brief example of this concept. If you take a bar with negligent mass and have 3 point masses on this bar separated by a distance of L over 2. To calculate the rotational inertia of this, you first start with our equation I equals the sum of mr squared. You plug in the different r's of the different 3 point masses based on our axis of rotation along the far right point mass, and your equation yields I equals 5/4 ml squared. One application of rotational inertia is the conservation of rotational energy. This young boy is playing in the playground, as you can see, when he puts his legs in, he immediately spins faster. This is due to his center of mass now being closer to his axis of rotation, reducing his rotational inertia. Plugging that into the conservation rotational energy equation, half I omega squared, we can deduce that he will spin faster because the energy is maintained.